So a little bit of background on why we developed the Sea Gauge. Um, so as I mentioned, my background is primarily in parachutes, and the side projects that I like to work on are kind of pushing the state of the art in terms of wireless instrumentation, disreefing, commanding, and actuation of parachutes, and actually transmitting data from the canopy down to the payload and vice versa. So the problem that I'm typically trying to solve is that we have very limited in-flight measurements of parachute canopy elements. And that really does limit our analysis capabilities, and that really drives us to complete expensive and extensive drop testing. The image on the bottom right there is an example of our Orion parachute system drop testing. There we're extracting our drop test vehicle from a C-17 at about 35,000 feet. We've got tons of parachutes required for that test. They're very expensive, and one of the key pieces of data that we gather from those tests is the load uh, seen at the parachute riser, which is essentially just the sum total of all the parachute elements. It's a single value. But what we really want to be able to do is know what is the load in each individual element throughout the entire canopy, so that we can, optimize the design, reduce mass, reduce volume, all those things that us engineers like to do. So we have some heritage methods where we can make some assumptions on how we take that single riser load and divide it down and parse it into all the different element loads. But really, the vast majority of that is unvalidated. We don't have any in-flight measurements to say whether our assumptions are conservative or non-conservative or right on. Um, so um, the difficulty here, particularly with parachutes, is that we pack these parachutes into very small spaces. So any instrumentation is going to cause problems in a number of ways. Additionally, we want to measure the loads in the parachute without affecting the configuration of the parachute. It can be kind of detrimental to need to go in and sever a suspension line or sever a riser line in order um, to measure some of these loads. Additionally, the future of parachutes, or one of the future tools of parachutes analysis, is parachute fluid structure interaction, or FSI. So FSI is like the merging of finite element analysis, which is, the structural aspect of a stress analysis, if you will, with computational fluid dynamics, which is the fluid side of things. So, in the ideal world with enough computing power, we can run a full simulation that simulates how the air migrates around the capsule, creates wake, interfaces with the parachute itself and the lines, and then the parachute can deform according to that free stream air. The panels in the parachute will have contact with each other and simulate, the entire deployment and inflation of these parachutes. It's a very difficult problem to solve. Folks in academia are making really good progress. It's very exciting. We just don't have the measurements we need to validate these results. And if we were able to validate these results and use these simulations, we could reduce the amount that we have to spend on testing, and we could really try to answer as many questions as we can prior to the actual manufacture and test of the hardware, so that we have the most confidence we can. Now, we'll never be able to fully eliminate parachute testing because, well, it's fun, but there's just, it's not realistic to be able to model and simulate the entire process. But the more we can do on the computer, the less we have to drop. So what are some possible existing solutions for these questions? The question being, what are the loads in a parachute in its design configuration flying through the air? Well, so there's like standard inline load cells, which we've all probably seen. tension compression. This is an example here on the right from Futech. You can, screw on an eyelet on either side and put it in the middle of your suspension line. So you would cut the suspension line, interface it to the top and bottom of the load cell, and boom, you got a measurement. The issue with this that I'm trying to overcome is that this breaks the configuration. We need to actually deconstruct the parachute in some way to put this load cell in line. Another example of existing options is what I call a 3-point bending load cell. There's two examples here. This one, I call it a seatbelt sensor. This one's also from Futech. But then we've also worked with companies like this is Novatech over in the UK that uses a similar principle on a more cylindrical, if you will, rope. And the idea here is that the textile member that is in question is actually routed kind of out of the way of its kind of axial loading, such that when tension is applied on either end, the cord produces an out-of-plane force on some type of bending load cell, and you can measure or infer the tension in the rope based on the kind of sideways force that you're putting on your 3-point bending load cell. We've had mixed success with this. With webbing and straps, we've had some success. Cords, not so much. This approach really relies on the material properties of your rope or webbing or cord itself, along with the interaction of the material between the textile and the 3-point bending device, plus environmental conditions. You're really kind of inferring a bunch of things about the loading setup here to get your tension. Not a lot of success here with these cords. So this is a good non-invasive option because you can clamp it on. You don't have to cut the parachute up into pieces. But we've had issues with calibration and getting useful results from this. So we stumbled on our idea of just basically clamping on a C gauge, if you will, to measure the tension in a cord without breaking the configuration and without relying on that out-of-plane force between the cord and the load cell. So we call it a non-invasive textile tension measurement device. So we can install it on any existing system. For instance, if you walk into a wind tunnel, you're flying a parachute in a wind tunnel, ideally you could walk up and just slap this onto a suspension line and get a decent reading on your load in that suspension line. The shape of the gauge allows the cord to transfer the entire tensile load through the gauge. And I'll have a diagram that shows that on the next slide, but really we're avoiding that reliance on the material and the environmental properties. So we have this metallic C gauge. We put foil strain gauges to measure the bending in the device. And here you can see is a computer simulation of the deformation of the device as load is applied through either of the legs on the C gauge. And you can use your pre-calibrated bending values to determine the actual tension in the cord. And so we built one of these and demonstrated it using some Kevlar cord. I'll show that shortly. So here's a quick diagram of what it looks like in concept. So you've got your C gauge here in green. You've got your foil strain gauges here on either side of the span across there. And really the key here is that the center span of textile is completely untensioned. So no load is transferred through this cord. It's all kind of transferred through the C gauge itself, resulting in that bending. So there's no reliance on how the cord interacts with the C gauge itself. So here you can see our computer simulation and our calibration of the device. So this is a plot of the strain versus tension or simulated tension. We've got our linear relationship, and you can design this device really to any range of values that you like by scaling it or choosing different materials to build the sea gauge out of. And you got to make sure that, of course, your strain gauge is able to measure your max predicted strain, because you don't want to rip those strain gauges off of the device. You also need to take into account the yield and ultimate strength of the material that you're choosing in the sea gauge, because you don't want to deform that in a weird way. So one important aspect of this is, how do we interface the cord to the sea gauge itself? There's a lot of ways to do this, and we've identified a number of them. I think the most useful method would be to use what we call an outer friction grip. So this is a self-tightening attachment that grips the cord without damaging the cord. So the sea gauge itself, the metallic sea gauge, would have a cylindrical cutout, kind of in this direction on either side, and inside that cylindrical cutout is an insert that has a matching cylindrical outer mold shape, and the center of it would be some type of teeth or friction grip, so that as the cord is routed through here, and we tension it to either side, the force of the conical shape in the sea gauge kind of clamps down, if you will, on the insert, and the harder you pull, the more biting down force you have to hold onto your cord. This is similar to a cam cleat, like on a sailing vessel, when you run a rope through those two little rotating teethed mechanisms, and kind of the harder you pull on it, the harder it bites down. There's other ways you can do it. In this case, I'm calling it the inner friction grip, and this would fit inside the cord, and it's kind of similar concept with the conical shape, but instead of going around the outside of the cord, that conical piece would be inside, like a piece of braided Kevlar, and takes advantage of the constriction of these tension cords, so that as we tension the cord, it bites down on that stopper, which then gets interfaces with the conical cutout in the sea gauge and provides your stopping force there. Your attachment method can vary based on whatever your application is. Those, I think, are what I would call the more elegant solutions. We demonstrated this with a kind of less elegant but maybe more practical solution, and I'll describe that here. So this is our proof of concept testing that we completed back in 2016. So the cool part about this is it's a very simple device. This prototype was 3D printed aluminum. So aluminum's light. We didn't design it for a high load. This is a pretty low load test, but 3D printing it was pretty cool. So we've got our Kevlar cord that's in question on a tensile testing device. And we also have an inline load cell, like that Futech load cell that I showed on previous slides, inline here to validate our measurements. So we printed the device. We actually just used, I think, Proto Labs, which is just an online manufacturing house. It was dirt cheap. You get it real quick, so that's cool. So we got the device, we prepared it, we installed the foil strain gauge on it. We use an outer friction grip, so kind of that conical insert, but we also just tied knots in the cord just for this prototype testing, just to ensure that we didn't have any slippage or anything. Obviously, you can't just go tie a knot in a installed parachute line, but there's other things you can do that are less elegant that might work, like zip tie type things to clamp down on the cord to interface with the kind of interface of the sea gauge there. But anyway, we use these outer friction grips and the knots, and we did this low load tensile testing here at JSC. We did some kind of random actuations to kind of simulate parachute loading, kind of cyclic loading. So this is a plot of strain over time, so the time history of the output of both of the sea gauge and the validating inline load cell, which is in orange. So you can see that we've plotted the inline load cell on top of the blue C gauge output, and you can see that we very nicely match the peaks. We have a couple little outliers here in a couple spots. We didn't really dig too deep into that, may have had a little slippage, but in general, we had outstanding matches over the length of this test. I'll just pause here for a couple seconds. All right. So that's the bulk of the information here. So I just have a couple of summary slides, just kind of wrap it up. So the current state of the art in this type of instrumentation does have some shortcomings for the applications that I care about, and probably a lot of you care about. With those inline load cells, you have to modify the system to get that load cell inline of the load. That will break your configuration if you're in some type of qualification campaign. It might also affect your actual measurements since you are modifying the lengths, the weights, the densities of your system. There's also 3-point bending devices, but that relies on the elasticity of your cord, the other material properties, and how the cord interfaces with your 3-point bending device. And another point here is we know that some high strength cords like Kevlar do have properties that change over cyclic loads. So there's plenty of information out there that shows the change in modulus of a Kevlar cord over various loading cycles. So that can really hurt your calibration and your accuracy in your final measurements there. So what makes a C gauge different? Well, we can go install it on existing systems that are already built without having to cut or disassemble the lines. The gripping system ideally does not damage the cords, so it's non-invasive. You can put it on, you can take it off, and keep testing your system. This calibration only needs to be done once. So since we're routing all of the load through the C gauge, there's no dependence on material properties. So you calibrate your device, you get a cal sheet for a particular serial number, and now you're good to go to use this on whatever system you'd like. Finally, this design can be easily scaled in size, in thickness, depending on with different materials. So we initially chose aluminum 3D printed for our proof of concept, but you can use any number of materials to measure larger, smaller loads and to optimize the mass and size of the device. Some potential applications have been identified. It's mostly in industries that care about tension in elastic or textile cords, but we can modify the concept for various applications. So here's an example of a concept for measuring some straps or webbings. It's basically the C gauge, but extruded to be a little bit wider, but the same concepts apply. At NASA, we would use this in parachutes, spacecraft uprighting bags. So for instance, when the Orion capsule lands in the water, big inflatable uprighting bags are deployed to ensure that the vehicle is in a stable upright position. So analysis of those bags would heavily relies on measured tensions in various cords and members that restrain those bags. And then also we've got inflatable structures, inflatable habitats for kind of long duration space missions. And this could go into the design and testing phases of those items. On the industry side, these could be used in basically any application where you want to know the tension in some member without needing, and you don't want to break the configuration. So sailboats, if you rig up your sailboat with a number of these across all the various lines, you can have a good overview of how your system is performing in the various wind conditions, whether in a design and testing phase or even in an operational environment. Climbing, inflatable buildings, rigging, crane rigging. So this is kind of an interesting one. So our initial concept here is primarily for textiles, and we demonstrated this on a textile cord. But this concept could be used on metallic ropes, if you will. Um, it would take a little bit of work to ensure that you're offloading the center span of the rigging completely, or account for the amount of load that is transferred there. But in theory, this concept would apply there. And then, of course, seatbelt testing with the standard seatbelt sensor. So in summary, the current state of the art of measuring loads and cords currently requires permanent mods to the target line or accepting significant calibration errors. But this C gauge resolves both of these problems, allowing for consistent and accurate measurements without permanently modifying the system. So we built and tested this prototype. We had great results matching the inline load cell, and I just touched on some potential applications in the commercial sector.